Let's discuss a question on theory of machine. This is from vibration. We need to calculate uh, the natural frequency of the system. Okay, so and in ideal case, you have a bar and you have a torsional spring at the in the middle. So we use a regular the regular conventional force method. So what we do is, if you remember how we used to calculate the natural frequency for the spring, we used to deflect the spring by delta by x, and then from the equilibrium we used to deflect the mass by x, and then we used to write the equations for that mass, and then we used to solve. We used to just write sigma f is equal to ma, the Newton's law for that, and we used to get the we used to express acceleration as something some constant acceleration as something of displacement. Okay, and this used to be the natural frequency whole square. So this is the conventional format. So here also we will, because the angular displacement, it has a degree of freedom in the angular sense, so we will just displace, this is the actual body, so we will just displace this bar by theta. Okay, so this is theta and therefore this is theta. I'm just drawing it by one line. So this is my mg, and half of the mass will be acting here and another half of the mass will be acting here. Okay, and this, okay, so the thing is that this, okay, so let's call, okay, so here you have a torsional spring. So when I deflect by theta, the torsional moment, the torsional resisting moment will be k into theta. That is also I need to apply when I deflect by theta. Okay, so this is my force diagram, and okay, so I'm applying everything in angular sense. So sigma m is equal to I alpha about the point O. This is what is, now in a linear sense I will apply sigma f is equal to ma, which I do for springs when I calculate the natural frequency of the spring, but this is the angular sense. So summation of moment about O. So mg by 2 is this force. Now we are calculating moment because of this mg by 2. Now this length is basically half of, so this entire half is L by 2, and mg will be acting at the half, at the center of each half. So it is this distance is L by 4. So L by 4 into this vertical will be cos theta. So L by 4 cos theta is the moment due to this right side mg by 2. And this mg by 2 will be negative, it's anti-clockwise, we are considering clockwise positive. So the direction of theta is in this way, so alpha also I assume in this way, and that's why moments also I'm taking in that way. So minus mg by 2, this will be again L by 4, and this will be, because this distance is L by 4, into cos theta. Okay, and this k theta is also resisting, so minus k theta is equal to I alpha. Now I is mass moment of inertia about the center. About the center we know it's ml square by 12. For this is something which we derive, you have to remember. So this mg by 2 gets cancelled, it's minus k theta, and alpha we know it's theta double dot, okay, minus k theta. So theta double dot will be minus 12k by ml square into theta. Okay, so same thing, whatever you express in this format, comparing with this format, omega n is root 12k by ml square. 12k by ml square, that is my omega n, and my linear frequency in terms of cycles per second will be 1 by 2 pi omega n, which is 12k by ml square. So this is a very simple problem. Only thing is you have to just draw this free body diagram after displacing by angle theta. So draw that and just write this in angular sense. This is the conventional force method or the moment method. In terms of spring also we do the same thing, but we apply sigma F is equal to ma and then bring entire thing in this form. Okay, so the answer for this is 12k by ml square. The answer is C for this. Thank you.